happen next? Now there is a pressures by the from that are working inside this bubble. So this is a P1 pressure, for instance. This is a P2. It is largest at P1. So, and this is the difference between them. Now let's compare this difference with the difference of the pressures outside. If, for instance, this pressure, this one, is larger than this one, and it is logically, because the flow moves in this direction. So now we have the differences of the external pressures. You see the difference here of the external pressure is directed on the right. However, the pressure inside the bubble is directed on to the left. If it is larger than this one, the bubble is stable and doesn't move. Is it clear? The flow is equal to 0. Is it clear? If the bubble doesn't move, means no flow, means emboli. And this is very dangerous for the human life. You know the cases about the cases of emboli because of vaccinations. Some cases there are in the world. So, but the emboli became was resulted because of the thrombocyte aggregations. So, but this is actually the same. The aggregate of the thrombocyte can be considered as the spherical particle within the blood vessel, and so we have the emboli. So, if you don't have the questions, we come to the next very large topic that will move us through sound, with a very simple aim to understand the physical fundamentals of our speech and our hearing. We'll spend here maybe 4 lectures, we'll see. But this is a very extended topic. So first idea is again very simple. When we speak, and if you have some defects of speech, this can be connected with the inability of our partner to hear us. If he doesn't hear, we are speaking loudly, or maybe the speaker doesn't hear himself. If I don't hear myself, I'm speaking also loudly. So that is why this is a connection in between the speech and hearing. And this is the reason that we go to consider both of them and the connections between them. So this is our formula. Speech plus hearing is equal to voice. No voice without speech, no right voice without hearing. However, to hear, we need the detector, the detector, our ears that we are listening, that accept the voice. So that is why, coming from the idea from speech plus hearing, we move to the instruments to generate the voice and to detect the sound. Voice definitely is a sound. But this sound can be generated by the human only because of breathing. If we don't breathe, we can't make the sound. Try to do, for instance, the sound ah without breathing. It is impossible. Try. No breathing and do R. Generate R. Please try. I don't hear.
It's impossible.
It is impossible, yeah. So that is why we need to connect the generation of the voice with breathing. So this is the other physics. Sound generation is clear to us how to do from general physics, but in medical physics, we are considering generation of the sound because of breathing. So we go to consider generation of sound, the traveling of sound, the parameters of sound, and how the sound has an interaction with our air. When we speak about breathing, we consider the air channels that air travel through the lung to the trachea, to the mouth, and to the nose cavity. So this is our track. We don't consider the track that is here, because definitely air is traveling here too, or transmitted here too, but it doesn't work to generate the sound, because the sound generation, the voice lungs are located here. So that is why we are interested in this way, in this path. So the main topics: the sound, the voice separate, the hearing separate, analyzing of the sound and speech and centering of them, and treatment of the speech, treatment in brackets, because we are not the doctors, the medical doctors, but just to approaches using the technical instruments. And very shortly about the sound for medicine, because we have the topic on medical diagnostic, physical diagnostic technique and methods, and in this course we consider sonography very widely. So this is our plan to life. And now we go to our first topic. So the sound. If I ask you, what does it mean sound? Okay, please try to explain me. What does it mean sound? What is the nature of sound? Can you tell me?
Svārstības.
Kam? Oscillations.
Gaisa svārstības.
Gaisa svārstības. Tikai
Nu,
gaisa
garam
svārstības.
veidā.
Vides svārstības.
Vides svārstības. Okay, so the oscillations by some environment, okay, some matter. More precisely?
Nu, skaņa izplatās garamviļņu veidā.
No, this is a technique how to transmit, but I am speaking about the nature.
Nu,
Svārstības, it is true, but so more precisely?
Periodiskas svārstības.
Definitely periodiskas, yeah.
Skaņa ir sava frekvence.
Pardon?
Skaņa ir frekvence.
Skaņa nav frekvence, skaņu mēs varam izmērīt, izmantojot frekvenci.
Balsnes svārstības.
Kā lūdzu?
Balsnes svārstības.
Ne, kāpēc jūs tā, kas saka, zakliņeli, ja, uz vārdu svārstības? Es lūdzu precīzāk, tas nozīmē svārstības pareizi, bet es lūdzu precīzāk.
Nu, izplatās dažādās vidēs, cietās.
So you're
Citrās
speaking about the
krāsveids.
transmission directions and no. Okay, let's go to the experiment. So this is the experiment. What can you say now? What does it mean sound? Is the experiment clear? This is so-called fork to generate sound. It's excited, so these whiskers are oscillating, and what we see because of these oscillations, what do we see? What do we see?
Deformācijas.
Exactly. There is a deformation of the matter. So that is why we can say that sound means deformation of the environment of the matter where sound propagates through. Is this clear? Oh.
Yeah.
Does it get it?
Yeah.
So now let's go to consider the structure of this material where sound propagates. So if you get the microscope, we can see, more or less see, if it is very well microscope, we can see single atoms that are connected by the bonds. What is the nature of this bond doesn't matter, but definitely there are bonds between the atoms. If we don't have the bonds, the atoms can't be connected and the matter can't exist. So that is why really there are bonds inside. So now I deliver the pulse of sound, the very sharp pulse. Definitely because of our deformation idea, the atoms are shifted from their initial positions. We have the deformation of the bond. Means this is the beginning of deformation. If I get off this pulse, the deformation will go ahead, will transmit definitely, like in the gale. Something like this we see. So our conclusion here is very simple, that propagation of the sound is a propagation of deformation of the environment. Is this clear?
Jā.
So now we can provide the image of this one, so the diagram of this propagation. So this is the force that is delivered by this pulse, and this is time. So this is the force, the pulse, and this is the deformation, just one pulse. At this cross section, we have such a pulse of deformation. Next, the pulse is moving ahead, and it is already here. Next, it's here. So at these cross sections, we have the propagation of the deformation pulse. If we deliver the negative pulse, means in different direction, in opposite direction, definitely I have the same as before, however, at the negative direction. So I have such a propagation. Now I deliver the doubled pulse, fore and back. So now I need to connect the previous two experiments, up and down, and up and down. Is this clear? Vai tas ir skaidrs?
Jā.
If I go to deliver non-stop pulses, I have non-stop propagations here. So for the first cross section, it is the first pulse. The second cross section a little bit later. The third cross section a little bit later again. So I have such a diagram of propagations in three cross sections: the first, the second, and the third. Like this one. One more. Is this clear? Questions? Oh.
Ir skaidrs.
So from this very simple diagram, we can conclude that this time interval when the deformation pulse decay or is delaying the first cross-section pulse is some specific time, and it is actually for the third cross-section must be the same time but the double time, like this one. And this is a specific really. And now have a look, because this time interval corresponds to the cross-section. This was the first cross-section, second and third, means this time corresponds to the distances. And if I know the distances and I'm able to measure time, I can calculate the propagation velocity, A to T. So this is the sound propagation velocity. At the atomic scale, at the macro scale, if I go to calculate, to measure the distances at the macro scale, so I need to know the single distances and to multiply with the number of these steps that sound propagates. And to measure the time of propagation, so I have finally the velocity of sound propagation, of the deformation pulse propagation. So now we're back to the same diagrams that we started from. And I see that the deformation here, the complicated, can be distributed in two directions. The horizontal one means the deformation pulse propagates this direction, and the vertical one transmits this direction. Actually, we have in this case two waves of deformation, or two waves of the sound. So this is a transitional and this is transversal wave. So really we can describe the propagation of deformation, means sound, in two directions, and to say there are two waves, transmission and the other wave that is in perpendicular. So if you go to analyze the oscillations of the bonds or atoms, we can find the oscillations in both directions, the horizontal transmission, vertical transversal. This is the idea to conclude that the propagation depends on these bonds, means depends on material, depends on environment. Moreover, if you don't have the bonds, we don't have propagation because we don't have deformation. The absence of the bond means what is the environment that doesn't have the bonds? What is the environment that doesn't have the bonds? Please tell me.
Gases.
No. If it is true, we are unable to hear sound in atmosphere. But we hear.
Tad vakumā.
Exactly. So in vacuum, vacuum environment doesn't have bonds in between the particles of the vacuum. In vacuum conditions, really, the particles are distanced at the very long distances, and that is why they are unable to provide the bonds. And this is the reason that sound doesn't go through vacuum. So this is the situation when the transversal bonds are absent. We have just a transitional one. This means that the sound will go this direction and doesn't go this direction. So this is example, the diagram that explains what is happened. So no sound, no deformation, now sound propagates, and we have higher density of the particles here and less density here. So it means this is a positive amplitude and this is a negative amplitude. The distance in between the increased densities or decreased densities is so-called wavelength. I believe that you know this very well. So this is the center of sound generation. The sound is generated spherically in all of the directions. The environment here is very homogeneous, means no anisotropy of the bonds distribution and the forces in between the bonds. So this is the first pulse of sound. The second pulse is generated, however, the first one propagated here, ahead. So now the first is here, the second is here, and this is already the third generated. So our conclusion, oscillations means the wave. We know this. The wave means the sound. The deformation transmits. This means the deformation is a carrier of the energy, because if we have deformation, this means the energy is changed, both potential energy and the kinetic energy. Potential of the bonds and kinetic of the deformation propagation, because deformation has a velocity. So this means the very simple conclusion and very important, that the sound wave is the carrier of the energy. The question, please. Are you here?
Nav jautājumu, viss
Nav
skaidrs.
jautājumu.
Okay. The sound wave is the carrier of the energy. The sound wave is a running wave. It runs ahead. So again, our diagram, the wave, the second wave, the third wave, they are running. Oh, not right animation. Oh. Good. Now it is right. Propagate ahead, running wave. The deformation, if we have deformation, means there is a pressure at the area of deformation, mechanical pressure. If the deformation has oscillations, means the pressure has oscillations. It's logical. If deformation propagation is the sound propagation, means the propagation of the sound or the sound itself is a result of the oscillating pressure. So that is why you can say that the sound wave is the wave of the oscillating pressure. This is a key word of our physics, pressure. So that is why, again, the sound is the oscillating pressure. So, some summary. The sound is the transitional wave. It is a running wave. Propagation of the sound depends on the environment. The sound wave is an oscillating pressure wave. The sound wave is the carrier of the energy. No questions? If you have some questions, please ask.
Ir skaidrs.
Now I'm going to speak about the sources of the sound. The key word again, just to remind you, is the pressure. If you speak about pressure, and if we keep in mind that our voice may be generated only when we have breathing, means breathing gives the sound, and the sound is the oscillating pressure, means we need to deliver the air flow like the oscillating flow. If, for instance, the sound has a frequency 100 hertz, so we have to press with the same frequency. Is it right or not? Is it true? Are you breathing with this frequency, 100 hertz? Hello? Lūdzu, jūsu viedoklis.
Man šķiet, ka nē.
What is the frequency of our breathing, approximately?
Nu, 440 hertz varētu būt.
No,
Nu,
no,
varbūt garāk bišķi.
no, no.
Nu, zem.
Mēs
Nu,
jau velkām
440.
kaut kādas 6 līdz 10 elpas minūtē, ne?
Ok. Jā, tad cik liela frekvencija? What is the frequency of breathing? If you're breathing, for instance, 10 times per minute, 10 times per second, 60 seconds. The frequency is 1 to 6.
Hertz. 1 to 6
Yeah,
hertz.
less, even less. But we need to get the sound with the frequency 100 hertz. So this is a huge question. How? We said we need the air flow from our lung, but this flow doesn't have the frequency that we need for the sound. And this is a contradiction. And we try to explain this. So this is, as we have discussed already, this is breathing, this is a flow of air, and we need to reach the frequencies, and how, we don't know until now. So our aim is to explain this question. How? How, because of breathing with a frequency less than 1 hertz, we can give the frequencies 100, even more. For this, we go to consider the models of sound sources. Before this, we need to know the Bernoulli law. The kinetic energy plus the potential energy is a constant, and he had applied this for the flows. This is a Bernoulli law, that the static pressure is a half of the density of the flow with the velocity in square power of the flow, and this is a constant. So we know this already. The model of the sound, the Wilson. So it is located at the air that is under the atmospheric pressure. This is a normal pressure. Now I'm pushing the flow inside the airflow because of breathing. Pushing in, the flow is going through this pipe. Have a look. There is a pressure here, inside, definitely. But what about the pressure here at this end? Before the flow comes, we didn't have the velocity here. It was equal to 0. This means that the pressure here was equal to this atmospheric pressure. Now we have the flow. As a result, the velocity is increased. And following the Bernoulli law, the pressure must, what? If the velocity increases, what must be happen with the pressure?
Pieaugt.
Pieaugt?
Jā.
Kritīsies. Vai tu ne?
No, Bernoulli law. V uz augšu, P. If the velocity is increased, what about
Kritīsies
pressure?
spiediens.
Kā lūdzu?
Spiediens kritīsies.
Tieši tā. Moreover, a little bit velocity increases, this is a square power, significantly the pressure falls down. So this means in our model, when the flow appears here, the pressure here decreases significantly. It falls down. So when this pressure increases means the flow goes out. The velocity increases and the pressure falls down. So, if so, this pressure is less than the atmospheric one because it was fallen down from the atmospheric pressure level. Means it is less than the atmospheric. If it is less than the atmospheric pressure, the air around is moved from the surrounding atmosphere to this point because pressure here is less than here. Finally, this pressure is increased and will become equal to the atmospheric pressure. What we have next, we continue to press the air from this pipe and the entire process will repeat. We have the oscillations of the pressure here. Is this clear?
Yeah.
If there is an oscillation of the pressure, this means there is a sound. So the sound is generated because of the pressure oscillations here. And the oscillations here may be delivered at the very high frequency. Means the sound is provided with the high frequency. So now the diagram of the pressure, this is the atmospheric pressure. From the beginning, when we are pushing out air, the pressure here increases. After that, pressure P falls down because of the Bernoulli law, even to the negative values. Again, rising up, and so finally we have the oscillations of the pressure P. So oscillations of the pressure means sound. The sound is the oscillation of the pressure, means this instrument, this wheels, is the source of the sound. This is the sound. Is this clear?
Yeah.
Where are the sources? Here. And even here. So we can use these sources to communicate, but we can't speak. For instance, yeah, we can communicate, but we can't speak. means this source isn't enough to provide the speech. Moreover, if the velocity here is very high, the flow is separated into the single flows. There are cycles of these flows, and this is a turbulence. We know this phenomenon. If it is a turbulence, we have the noise. So we have considered the turbulence noise at the previous lesson. Actually, this is the noise of the turbulence. This is the noise of the turbulence. Means we can communicate using this turbulence sound. This is a turbulence that I'm worrying about something. For instance, a dog is worrying. This is the sound, the turbulence sound. But we can't speak. So the next source, like this one, have a look. We push sound inside, and here immediately the sound is separated into two subflows. Means immediately we have the turbulence. This means that we communicate using this turbulence flow, turbulence sound. But the velocity here becomes higher. This means the pressure falls down. If the pressure falls down, following the previous model, we have the oscillations of the pressure. If there are oscillations of the pressure, we have oscillation of the, we have sound. So, two ways to use these wheels is connected with the turbulences provision and oscillations of the pressure. So we have sound. The turbulence also gives sound, where we have the turbulence here and here. The turbulence is here in trachea. It's a pulse length, sound length. Yeah, it's somewhere here. Turbulence. Turbulence. And here also turbulence. And here. Different options for turbulence. So the next one. The next one we go to consider next time, because you need to have a break 5 minutes, and after that you start the test. The questions, please.
Nav jautājumu.
Okay, so when the test starts, I'll be online, for instance, 5-10 minutes. If you have some questions, please ask me. And after that, I'll be disconnected and waiting for your results behind the screen. So 5 minutes break, and 9:10 you have the test.